Okay, there is several more algorithm. Last time we discussed together. We already looked into the example together. Especially the most important, you need to know how to measure or to determine the waiting time and also turnaround time. You need to know how to differentiate which one is your turnaround time, which one is your arrival time. After you get this, then you can calculate the average. If you still don't know how to measure the arrival time and turnaround time, so please try to do all the exercise and example given in the slide. And there is several algorithm, but most of that, the famous one is, I guess, FCFS and also round robin, because it will be continuous until the end of the module 5. But throughout, please make sure you know all the algorithm, how to use the method. First come, first serve, SJF, RR, parity scheduling, and now we're going to look into the last one, which is multi-level queue scheduling. In this algorithm, we're going to apply also FCFS and also RR, round robin. That's why you need to understand FCFS and round robin first before you can further go to the multi-level queue scheduling. Okay, because you're going to apply FCFS at like lower, higher priority queue, and RR for lower level, but it's depend also on the question. As long as you know these two, then you can understand and apply the method for the question and the multi-level queue. So the video I provide you is parity scheduling, and now we're going to start with our last algorithm. Okay, multi-level queue mostly is going to be under hybrid environment. And when you have a multi-level queue, ready queue is partitioned into separate queue. Example, let's say you're going to separate into high priority and low priority. So you have two, going to separate it into two. And mostly we can also name it as a foreground, which is the interactive, and a background, or maybe you can call as a batch. And you're going to have these two queue before you can submit it to the CPU to process. So mostly we're going to tag this first, and then for the background, it's going to waiting the foreground to finish first. Then it's going to continue. But it's depend also, because you're going to have another 4 method to be applied under your multi-level queue. Process permanently given in a given queue, and each queue has online scheduling algorithm. So you can see here, you need to know RR, round robin, and first come first serve, FCFS. If you don't know, you cannot apply. You cannot also solve the multi-level queue quiz. So please remember that foreground using RR, background using FCFS. But sometimes in equation also it can swap and switch is other. Depend on the question. So please make sure carefully read the question. Which method will be applied? Scheduling must be done between queue. So fixed priority scheduling. Serve all the foreground, then from background. So you're going to do the foreground first to pass to the CPU, and then after that your background. Time slide. Each queue get a certain amount of CPU time which can schedule amongst its processes. So when you try to wait or waiting here, that's why you have a possibilities for a starvation, which is you need to wait quite long for foreground to finish. Example, 80% to foreground using RR, 20% background in FCFS. Okay, here under a separate queue for each priority, you were given also with the priority. Now you have 4 level. N level. So it's depend on the priority, and you can see you have several process inside to pass to your CPU. So work in conjunction with several other scheme. Several other scheme is like your FCFS, your RR. Work well in system with group, job group by common characteristics. So you have a several. Now let's see the example first, then you can understand more depending on the 4 method I already mentioned to you. You have a 4 method. First method, no movement between queue. When you have a 2 queue here, let's say you have job 1, job 2, job 3, job 4. And here is your CPU. You're going to pass. So in between this queue, there is no movement. So you finish this first, pass to the CPU, J2 first, and then J1. After finish, then J4, and then J3. It is when you have no movement between the queue. But you have another methods when you have movement between queue. Might be you can have J2 sent to the CPU first, but you have like a quantum, so it's not finished. Then you can move to your to your low priority, which is another queue. This is like higher priority, low priority. So it moved to another. Might be J4 will move to here. So you can see it having a movement. Later on, you're going to see the example so you can see clearly, okay? Another one is case 3, method 3. Variable time quantum per queue. So you're going to apply a quantum things in the method. And lastly, edging. So edging is you need to wait. Sometimes it's quite long. So it is under method 4, edging. Let's see the first case, which is the most simplest one, which is no movement between queue. So it is a simple method. Reward with for the high priority job, because it's going to priority the first priority. After finish, then you can move to another. So processor allocate using FCFS. You can see here, although it's mentioned that foreground, which is the active one, the high level is going to use RR, but sometimes each method they have their own. Okay, so here under case 1, you're going to use FCFS at the processor. So here high, low, let's say. So you're going to apply the FCFS first. Processor allocate to the lower priority job only when high priority queue is empty. Means that after it's all finished, then you're going to go for the low priority of job. Good environment, which is few high priority jobs, spend more time with the low priority jobs. So let's see the example here. We already have 5 jobs altogether. Arrival of the job is similar, but in the question it will mention to you which one is the high priority, which one is the low priority. So assume that the high priority is J2, J3, and the low priority is J1, J4, J5. Okay, in question it will mention, okay, which one is the high priority. And there is no movement between each other. Means that, okay, this one will be go first here in your CPU. It's going to process first. After J2 finish, J3 will be replaced. After J3 finish, then you can move below, which is the lower priority. So higher priority must finish first, then it's continue with J1. Awak semayang apa? Bukan main laju. J1, and then after that J4, and lastly J5. Okay, while if you have another one cases which is method movement between queue. Processor adjusts priority assigned to each job, which is high priority job. Initial priority favorable, treated like other job afterward. Quantum interrupts can be also occur. Job preemptum, which is moved to the next lower queue. Means that when you have the quantum CPU, okay, let's say you have two, okay, two je. One, J1 and J2. Let's say for J1, this is high priority, this is low priority. Let's say you have a quantum equal to 4. But your J1, let's say, have a 5. 5, and J2 have, it doesn't matter, I guess, for 3. So here, when you move J1, because this is high priority, you're going to move J1 for to the CPU first. It's going to handle the J1 first. But you are having a quantum. Quantum interrupt is occur, so it's only 4. But our J1 having 5. So you're going to have the balance of 1. Where it's going to go? It's going to go to the lower queue. So J1 will replace here. J2 will finish at the CPU. Then J1 will be enter. So may have a priority increase. Good environment for interactive system. So let's see the example. You have similar example like previously. You have 5 jobs all together. And the CPU burst is already given. And the time quantum. Now the time quantum for high priority is 5. You have the CPU burst. So let's see the okay, let's see here. We have the high priority is J2, J3. Assume in the equation mentioned that J1, J4, and J5 is lower priority. So what we're going to do? J2 will be handling first at our CPU. Okay, J2 will be handling first. Now our J2 having the CPU burst is 10. But we have the time quantum is total at 5. That's why we're going to deduct, we have a balance of 5. Where it's going to move? It's going to move to the lower queue. So from here is handle first and another 5. Another 5 reminder will be moving here. Let's say your J2 are having a 9. So you're going to have another 4 here at J2. Okay. So when it's already goes to here, J3 will replace. Okay, J3 will replace. Lajunya. J3 will be replaced here, and you can see J3 only 4. It is a fewer than time quantum, so it can finish all 4. After J3 finish, who going to replace? J1. J1 is 5. After that, J4. J4 is 2. And then J5 and lastly your J2. Okay, it will follow by. This is happen when you are having a movement between queue. Means that from high parity, you go to the low parity. Later on also, you can see under edging, you can also having a movement between each other. You're going to move this low parity to high parity. So it is a movement between queue. Okay, now we're going to see another one. Case 3, variable time quantum per queue is a variations of movement between queue. Each queue given time quantum size. Just now you can see it's depend on you. Sometimes it's give you at the high parity for the time quantum or might be at the lower quantum. But here you can see each queue will be given the time quantum size. Means that you have for high parity and low parity, they have the time quantum. That is under variable time quantum per queue. Size twice as long as previous queue. So it's going to be twice from the previous queue. Fast turnaround for CPU bound job. CPU bound job execute longer and given longer time period. Improve chance of finishing faster. Input-output bound job, just as printing a series of documents, have many brief CPU bursts and long input-output cycle. So CPU bound job, just as finding the first 300 prime numbers, have long CPU bursts and shorter input-output cycle. So let's see the example here. Similar also, let's say it's continuous like from previous. We have the time quantum of 5 for the high parity. And for the low parity, we have time quantum at 10. You can see it is a double. Twice or a double as a previous queue. Okay, over here, firstly, you didn't see like this because it's having here. But you can see it's going to be go to this CPU and you have a reminder of 10. Now you have a reminder of 10. You're going to move to the lower parity. For the J3, it can finish because it's 5. The rest is also can finish on time, which is time quantum is 10. So it is follow a sequence. J2, and then J2 goes below at 10, and then J3 J3, continue with J1, J4, J5, and lastly, your J2. For the last case, which is case 4, which is edging, giving special treatment to jobs that have been in the system for a long time. Ensure lower level queue job eventually complete education. System keep track of job with time. If too all, so system move job to next higher queue. This is happen just now. I give you example. Sometimes from lower queue you can move to the higher queue when it is too long waiting. Continue until all job reach to the top queue. May drastically move all job to the higher queue. Just now is similar. So the advantage is guard against indefined unwidely job postponement. So here is the example of edging. You are having a similar this one is J1 and J2. Arrive first. Arrive job at T0. T0 you have J1 and J2. And it's depend also in the parity. If the parity J1 is low, so it's going to go to the low. If the J2 is high, so it's going to go to the high parity. Normally in question it will mention which parity is it. So here you have Q1 J2. So you are having 100 for CPU burst time. So imagine you need to wait 400 before the J1 can enter. So while job 2 is running, suddenly you have another at T50. It is half, okay? At T50, a new job arrived. J3, J4, which is also assumed to be low parity, while your J2 is still running. So because of this, you're going to see, okay, at T70, new job also arrived, but now you can see it is high priority, but J1 is already too long waiting for J2. Supposedly J1 will replace J2 because after this CPU will know, okay, after J2 complete, J1 will replace. But at T70, suddenly new job arrive. CPU already planned that J1 will be replaced J2 process after this. That's why you cannot just directly pick J5 after this because this is high priority, right? So supposedly J1 will do first and then J5. That's why J1 will, because it already has been waiting 70 CPU burst time. So that's why it will move to high priority. Then J5 will be put after J1. Okay, this one is important. You cannot put J5 first because J1 is already wait too long. And CPU already know, okay, after this I'm going to hand off to J1. Suddenly at T70, J5 is arrived. So you cannot assume that, oh, of course it is high priority, but because J1 is already wait too long, so you need to handle J1 first. Then followed by J5, J3, and J4, following their priority. Okay, here is the table of summarizations of all the algorithm we have since last time we learned FCFS, SJN, parity scheduling, SRT, round robin, multi-level queue. So you can see which one is the algorithm can apply in which best for batch, like interactive batch or interactive. So you can see which one, the disadvantages and advantages, and the policy type. This policy type normally we will look into at each earliest description on each algorithm. So it is not just and that, we have another one which is multi-level feedback queue. A process can move between the various queue. Edging can be implemented this way. The idea is to separate process according to the characteristic of CPU burst. Multi-level feedback queue scheduler defined by the following parameters. First is number of queue, scheduling algorithm for each queue, method used to determine when to upgrade the process, method used to determine when to demote a process, and lastly, method used to determine which queue a process will enter when the process needs service. Okay, you have example here for the multi-level feedback queue. You have quite similar when you have a several queue last time. You have here 3 queue. Last time we looked into like 2 queue only, high priority, low priority, high priority, low priority, right? But let's say here we have 3 queue, Q0, Q1, Q2. And it's mentioned here, round robin with time quantum 8 millisecond for Q0. So you have quantum 8. And you're going to use the round robin's algorithm. For RR, still for Q1, still also using RR, but now your time quantum is 16. The last one you are using FCFS. So it's already mentioned here, so you just noted all. Scheduling, a new job enter Q0 which is serve FCFS. It's mentioned, okay, under a scheduling. When it gains CPU, job received at millisecond. So it is under CPU. So you're going to pass to your CPU. If let's say it does not finish at millisecond, let's say you have job 1 equal to 9. So you have 9. What you're going to see, you have quantum 8. So you have a balance of 1. Here, you're going to move to the lower queue. So that's why you are having the connection, like a connection here, you're going to pass. So you're going to pass to the next queue, which is Q1. At Q1 job is again serve FCFS and receive 16 additional millisecond. So you can see also here you have several connection with previous one, which is a double. Where is it? Where is it? So you can see it's double here now. So it's going to receive a 16 additional millisecond for the Q1. If it does not complete, let's say it's how much? 20, 20? I guess it's already not 25. Put 30. So let's say your job 1 having equal to 30. So from here, you still have a balance. It's not yet finished also. It's not yet finished also. You're going to move and pass to next. If not finished, it's not complete, you're going to move to the Q2. So you're going to move to the Q2. Process in Q2 are run on a FCFS, but are run only when Q2 and Q1 is empty after it's finished. This scheduling algorithm gives highest priority to any process with the CPU burst of 8 milliseconds or less, because you are using a round robin. So this is how it's going to be connected from each queue. When you have 3 queue, you can connect it together, but it depends on how many millisecond you have for the quantum, and then how many also you have for the CPU burst. If it is not enough, you're going to pass to next. If not enough, you're going to pass to the next, because you are using a round robin. So you know that it's going to stop or trigger a stop to go to the next job following the total quantum that available. Okay, this one exercise, I guess you can try, because over here for this CPU, okay, let's see together for exercise 5. Exercise 4, we have 5 process A, B, C, D, and E. It mentions that it's arrived at time 0. All okay. It's going to arrive at time T0 with different CPU bus. It's already mentioned here how much is have at each job, and priority level as well. So you still remember the priority level. So you need to also mention, assume the MFQ scheduling algorithm is applied with 2 level and priority range 1 highest. So it's applied with 2 levels and priority range 1 higher. After that, by given an initial time quantum for the first level is 5 CPU bursts, and last level using FCFS, you need to calculate, as usual, you need to find the waiting time and turnaround time. After you find the waiting time and turnaround time, you can calculate the average. Okay, let's see here. For the first, you're going to see you have the priority of number 1. Second, you're going to have job E. Third, you're going to have job A. Fourth, job C, and lastly job D. And you also have the quantum is 5. But here you can see you have also the maximum of 10. That's why later on you're going to move to the next queue, because it's already reached maximum of 5 bus. Okay, let's see how you're going to draw. First of all, you're going to have what? Job B. So this is the first job. And the CPU bus is 1. You have the quantum is 5. So second, you're going to have job E. And then job A. After that, okay, you can see job A. You have quantum as 5, but job A having 10. That's why later on you can see you need to pass this job B another 5 to next. Okay, but this one is just for first time. You need to know which one is the parity. And the parity last one is our job D. Now we're going to consider about our quantum. Okay, about our quantum. So for the job 1, it is 1 only. So it's still under below than 5. So it's okay. It can finish as soon as possible after it starts. Continues after that. Which one? Job E. Only 2. Okay. Job E. Only job E. Sorry. Job E is 5. Job E is 5. After that, we have job A. Job A is 10. That's why here you can see 10 minus 5, you're going to have another 5. But you're going to move it after that. Okay. Now, here you have 5 also. It's look like a bigger size, but it actually is similar size for here. 5 and 5. After finish job A, you're going to move to the job C. If you still remember, we have like this. Let's say your job B here, and then your job E, job A. And you have another one, job C, job D. CPU, run the job B, run the job E, run the job A, but 5. Where it's going to go? It's going to go after that, isn't it? Another 5. So similar also like this. So what you're going to do next is your job C. Job C, how many? Only 2. You have 2 only. And lastly, your job D. Job D only 1. Now you will continue with job A. Job A is going to be another queue because it's already just now like higher parity, low parity. If job A here, it's going to move to the next lower queue, isn't it? That's why you can see we're going to start with Q1, but it's actually continuous, okay? Only it's different queue. It is 15 until 20, altogether is 5. Then you finish. Now you're going to see that you need to calculate the waiting time and turnaround time. Similar also here is waiting time. But for the J, for A, job A, it's need to consider these two. Okay, you need to calculate it. Last time we did together on how to calculate, because you can see you have two things. After that, then you finish. That's why you need to consider also the waiting time here to start the 15 for job A, and here for another waiting time for job A here. This one we done already, and your turnaround time also you need to consider to look into. So here is the example. You can see job A, for your waiting time for job B here, it is a 0. Job E, waiting time is 1. Job A, after this we look into because you have 2. And job C, waiting time is 11. Job D, waiting time is 13. So now we're going to see the waiting time for job A. First, we have the waiting time 6 altogether. You can see, you wait 6 second or millisecond here, millisecond I guess. So you wait 6 millisecond and you finish until here. You need to wait another 11 until 15, sorry. 15, you start here, 15 at 11 here. So this is the waiting time. This one is your waiting time before you can start. Similar also here. That's why for 15 minus with 11, you have 4 here. 4 times 6, you have altogether 10 waiting time for your job A. Now that's one is waiting time. Once you get waiting time, you can add all together. You average with 1, 2, 3, 4, 5. 5, you're going to have the average waiting time. For average turnaround, so turnaround job B, we have the turnaround here is 1. Job E, turnaround here is 6. Job C, our turnaround is 13, and job D is 14. So you can refer to this. But for our turnaround time for job A, so for job A, which one is the last one? You cannot see just here because this one is not the last finish, but we finish at here. So this is our turnaround time for our job A. So you add all together, then you're going to average with 5. You get the average turnaround time. So turnaround time is also quite similar to the completions for all the job. But waiting time, just now I already mentioned when it starts. Okay, but you can see for job A, it's cannot just take this one because it start here but it's not finished. So you need to have another waiting time again. So you need to consider another waiting time. So lastly, you can summarize is that process manager allocates CPU among all users. Job scheduler assign job to ready queue based on characteristic. Process scheduler instant by instant allocation of CPU. Scheduling algorithm is unique, characteristic, objective, and application. System designer select best policy and algorithm. So after careful strength and weakness evaluation, so this is all the summarization under your all the methods that we have been through. So any question from all the method we have been through all together? Just now in your e-learning, I provide you with the video for the starting from here. Time quantum context switch, I guess. Yeah. Until your parity scheduling. So please make sure you continue watching the video because next class we're going to move to our chapter 6. In our chapter 6, we have another more algorithm need to be focused with, like Peterson solution. You have the synchronized hardware, mutex log, semaphores. So all of that also require you some theory, but I guess it's also having a small commands or coding that you need to apply also. After this, I'm going to upload the module 6 to your e-learning. So if there is no question, I hope that you can continue with the, where is the e-learning? Okay, you can continue with this video and scan your QR code here for the attendance for our class today. And let me check. 20 over 24. Is it 20? 20. Okay. So if there is no question, I hope that you can continue focus with your study, because most of you WhatsApp me, you cannot join class since yesterday. I don't know what happened. Some of you is not yet finished on holiday. Some of you just come back to UTM today. So please make sure you can focus because upcoming we're going to also have a test 2, and you can continue with your lab 2. I already shared the link for the submission. And remember the due date is on 15 May. Okay? Any question? Okay, if there is no question, thank you everyone. Stay safe. Selamat Hari Raya. Bye-bye.